My name is Professor Joseph Wunderlich, a professor of engineering, architecture, and computer science, and this is a brief lecture and an introductory course in computing, and start off here with a little bit of what I did at IBM, and then talk about some other historical things in the development of processors before we talk about more recent ones in the following lectures. So at IBM, I was a hardware development engineer and researcher, and we worked on SMP symmetric multiprocessing machines, USA and Germany. I wrote part of a custom kernel operating system, including APIs and a lot of test programs to test the prototype supercomputers. These were supercomputers, mainframe supercomputers. We had vector register units we could hook onto it and do numerical computations, as well as 1,500 very complex instructions developed over many years. We could connect many of these machines together in parallel sysplacs, 512 processors in the one machine. That was the main machine I was working on, the System 390. And we tested these things in VLSI circuit simulation and hardware test, as well as manufacturing. And then I did a number of different specific things you can think about here, if you like, switching from 32 to 64-bit processing at that time, also implementing IEEE binary floating point, which is the industry standard now, but IBM invented floating point. It was 16 to some power instead of 2 to some power in scientific notation. So I researched quite a few things, including branch prediction verification, multiprocessor systems, and then random number theory and a bunch of correlated ones that came up with this controlled randomness that they patented inside of IBM. And then you can see some of the details there of other things that I did. And this is something we go into more detail in other courses on the development of parallel processing enterprise servers. They were changed to networking. Had just become popular then, so the CEO decided to say everything we're doing is networking now. Large-scale networking enterprise servers. And detail there that won't go into now. Switching from bipolar to CMOS for a number of reasons. Primarily, actually, to avoid the cooling headache of the bipolar circuits that ran very hot. And companies, large companies and countries that run their governments with these million-dollar machines really didn't want the headache of the maintenance of all the cooling, and it really wasn't that much difference in performance over time. Took a little bit of a performance hit when I went to CMOS inside of IBM, but it was worth it for everybody involved. It's what the market demanded and the customers. This is a supplemental lecture to what we've already learned about CPUs and selecting processors in this introductory course. There's a couple key terms in here. SIMD means single instruction, multiple data, and that started a long time ago, although now we use it quite a bit more. We learn more about this in advanced courses that you can take with me past this course. You can read and hear about a little bit of that. And then MIMD machines, multiple instruction, multiple data. There's actually 4 Flynn classifications. These are 2 of them. The simplest is single instruction, single data. And then multiple instructions. Single data is more of a theoretical thing. I believe the systolic array. So the two main ones for parallel processing is the SIMD and MIMD. So you should know those acronyms. And there's a lot of historic information in these pages here. You can skim through it. I could tell you stories about the different things here, but many of it's from long ago. The IBM RS-6000, those were in Texas when I was working for IBM in New York, in the larger scale systems. And I did have some of what I developed ported to IBM Texas or Austin to run on the RS-6000. I supervised the junior engineer over the IBM intranet. We had our own intranet for the whole world, actually. Leased optical lines between the cities and under the ocean. Just noting here, Blue Gene. It's a notable machine. I'll let you look up some of these if you like. These are becoming more historical references now. But some very early work in multiprocessing, parallel processing was, in fact, at IBM. More you can read here about clusters and other machines and DEC and Hewlett Packard and other people doing things long ago. More reading if you like. Let's read some more here and some IEEE transactions. IEEE is the standard for most technologies, or that develops the standards for most technologies. This document is simply a list of Intel microprocessors from Wikipedia, and you can find that on your own. You can just see the evolution of the processor speeds and the number of cores. Not a lot of other details here, but just a general progression. You can take a look. And don't strain your eyes too much looking at all the details here. Or here, you can go into Wikipedia and find this kind of information yourself. Here's an example processor in the not too distant past, just a couple years ago, is the Zen core by AMD, Advanced Micro Devices. Two notable things here is the low power, which is certainly a very important trend. And probably a little more interesting is that the neural network prediction. So this is a novelty. Neural networks were not something that was in mainstream computing until recently. I made two of them 30 years ago. One was my master's thesis, put a patent application in for that. Began patent application for that with the filed the disclosure document. And the other was a neural network processor that I'll post a picture of here. Next slide. So this is worth noting here that there's a neural network in this. And so it builds a model of the decisions driven by the software code execution and optimizes what's going on based on learning what's been executing. And then it anticipates future decisions and preloads instructions and chooses the best path for the CPU. So that's not a trivial thing. That is a new thing to be putting in these processors. Here are the two neural network chips that I designed in the early 1990s. The first was my master's thesis. It was a single chip microprocessor, neural network microprocessor, a vector register kind of architecture like the Cray supercomputers at the time, but on a single chip to do the matrix operation and the multiply accumulate aspects of the neural network transfer function or neural network execution, typical models. And it also uniquely had on-chip learning. So I use a numerical method to implement the transfer function in a way that it could be done digitally and in parallel, whereas up until this point, at that point in 1990-ish, had been done the sigmoidal transcendental function that you need for learning. It needs to be continuously differentiable, smooth curve, and to digitize it, it had to have high precision, and you needed a lookup table or a math coprocessor. And so it was typically done off on another chip or even an analog circuit, but not in parallel. So that was the idea here, fully parallel on-chip learning, and filed a patent disclosure document for that. The second processor, neural network, neural computer I designed and built was based on the theory of a professor I had that was to build chips based on the biological function, the electrochemical response, firing of neurons in the brain, and the transient output voltage that comes out of the neuron after it fires, and to modulate that in different ways, and to change the dendritic tree that feeds into it in ways to control presumably learning later on. So this was a novel kind of thing at the time, and so I designed and built this chip. It's both analog and digital circuits, and that was my preliminary research until I got into robotics, and did later consulting in robotics, and worked a couple years for AI DuPont Children's Hospital for rehabilitative robotics for children with quadriplegia. So we made robotic arms and force reflection. So these are two neural network chips I designed long ago. Now this is a excerpt from courses I teach on machine intelligence, and a book that I've started writing, and some past research. So the first thing we do is we compare symbolic AI to neural networks before we go any further. And without really going into all the details of symbolic AI, it was the artificial intelligence of choice, or all there was actually in the beginning. And it still has purpose. It's special forms of programming to establish rules that lead to outcomes in a more efficient way, and you have heuristics, and you prune the search space, and inference engines, and expert systems are one type of AI, symbolic AI, and the old languages of Lisp and Prolog were set up for that, and use predicate calculus and reasoning. Now, present day deep learning and neural networks is a different thing. And so you use a collection of standardized decision nodes, your neurons, kind of like the human brain. I mean, it is, but it doesn't actually process just exactly like it, which you can see in my publications of top down, bottom, versus bottom up, and two different neural computer chips I designed with different ways. But so you have neurons and you have layers in your neural network. And it learns by modifying the strength of connections between the neurons to satisfy all of the training set. And the training set is a group of stimulus inputs and desired outputs. So you have that known for this type of learning, backpropagation learning. This is where you start with learning. And then you repeatedly present these exemplars in a training set of a set of stimulus and desired response until it learns to do all of them. And they can be contradictory kinds of goals where it's not intuitive. And so you should take some time and read through the examples here, and we're going to have a Zoom, if this is an online course, we'll have a Zoom session where we'll run the code and I'll generate these graphs and you can see the difference. But, and I have an example here of a non-machine intelligence case and a symbolic AI case. And take the time to read through that. If you've seen it before with me, then don't take too much time. And you can click on some of the links here and look what's going on, or run the Matlab code if you know where it is. If you've done it before, we'll do it together in class, real or virtual. And so you see this learning process that takes place. And sometimes when you have more difficult learning where you're actually trying to do something that the exemplars are contradicting each other in a way. So the settling to a learned state where it has the knowledge or has learned to do all four of these things, or however many things, and thousands now, it's a compromise where all the weights between all the neurons and all the layers of neurons are changed incrementally until everything is satisfied. And that's why you have multiple, or you have an input layer and a hidden layer and an output layer of neurons, and as many neurons as possible to do more complex problems. There's actually an optimal number, but and so you can take a look at that. And so yes, so what you see on the first page here is one example, and then the more difficult to learn example, and then scale it up to a little bigger problem. And again, we'll take some time and do the simulations and do these runs, and it's fun to watch it work in real time as the system learns. Now I'd like you to take some time and look at the Matlab code that runs this. Understand first the behavior and look at the steps here, numbered 1, 2, 3, 4, 5, 6, 7, 8 steps, and how this works without looking at the math too much. That needs to be derived in detail in another place. And then take a look at the Matlab code, see what's going on over the next couple pages here. Try to make some sense of what you're looking at. And we'll go through this. It's simple code, but it takes a little explanation if you haven't seen it before. So just stare at that a little bit. And take a look at the different architectures, the 2-2-1 and then a 3-3-1. So that's 2 input neurons, 2 hidden neurons, 1 output neuron, or 3 input, 3 hidden, and 1 output. Exemplars of the training set, and epoch is each time you present all of the exemplars in the training set. And then just some plotting here you can see in Matlab. And the error, back propagating the error each time you present a input and desired output, and then you get something that comes out of the whole network. Well, you have an error because in the learning process, there's just going to be an error. You're not going to always get what you want because each exemplar is trying to do something different. And so you take the error and you back propagate it and change the weights accordingly, and then you present the next exemplar, which may want contradictory things, so you're tweaking the weights in some other way. if you have enough weights distributed in enough places, it will learn. And just some of the details of MATLAB. Some of the functions have gone obsolete over time since I first wrote this many years ago. Now, in recent times, 2020, you can do deep learning and neural networks using the parallel processing capabilities of graphics cards on simple personal computers using Cuda. And so let's take a minute and just look at graphics cards development, starting historically, quickly moving to the present, and then drill down, take a look at Cuda. Go to NVIDIA's website. Cuda is developed by NVIDIA, and they have a tutorial there. I want you to take some time and try to learn about Cuda. That might be something you want to do a project on. This is part of introductory lectures on graphics, computer graphics, and we're starting with historical perspective out of a textbook we're using by Hennessy. And so we're talking about the evolution here, and some key things to note is the price changes and the performance and the rendering capabilities. Firstly, the prices. Originally, these were very expensive, tens of thousands of dollars for silicon graphics terminals. I remember in the 1990 it was approximately, in a research lab, AI DuPont Children's Hospital and Applied Science and Engineering Lab. We just had one of these workstations, and it was very expensive. And then coming down greatly in price for the basics of what you want to do in graphics to just on the order of hundreds of dollars. But now back up again for into higher numbers for high performance computer graphics, because now we have graphics processing units with a couple thousand Cuda cores. We'll talk about that, and you can use these graphics cards for what used to be considered supercomputing, and certainly for artificial intelligence applications nowadays. So the graphics card now is something completely different than it was originally. Not completely different, but certainly much more powerful. And then performance. So originally, and still somewhat to this day, people speak of pixels per second, vertices, right, per second of primitives. And there's other benchmarks you can use too for performance. You can use floating point operations per second. But most typically, when you're talking about graphics, gaming, you want frames per second, real-time kind of fast change of rendering. So frames per second, FPS, is what you want to get used to talking about. And then the third thing is what you could render. Originally, it was just wireframes to fill polygons and primitives, we call them primitives of different shapes, and you put them together. So now everybody expects, and you get full scene texture mapping. So our computer graphics, the architecture and the hardware has evolved from generating simple or from a simple pipeline for drawing wireframe diagrams to a highly parallel processing design with several deep pipelines. And so most of the students listening to this have heard of how the pipeline works. In advanced students, we design pipelines, parallel pipelines, superscalar processors. Well, a pipeline, if you haven't heard what it is before, you do certain things when you're executing machine instructions. And the simplest would be to fetch the instruction, then decode it, and then execute it. That's 3 stages of a machine pipeline, of a machine instruction cycle. And you can get up to the order of 50 stages in some of the pipelines on the CPUs over time. However, what we're talking about here is the GPU, the graphics processing unit on the graphics card, executing very specific tasks for graphics as part of the pipeline and doing these things in parallel. So yes, the GPU, the graphics processing unit, is different than a CPU. And for one thing, you can do some complex arithmetic floating point. We've talked about that in most courses that you've had with me to some extent. You can do a great deal of floating point on completely independent data in parallel for rendering and for the graphics. Then down below here, we see whereas CPU die area is dominated by cache memory, GPUs are dominated by floating point data path and fixed function logic. We also can use now, and often do, many people do, the graphics card for processing for things other than graphics at times. You can do artificial intelligence calculations. A lot of calculations you used to do in supercomputing where you need some parallelism, matrix vector kind of operations, or a variety of things you can do now. And so you see this acronym GPU for general purpose processing on a graphics processing unit. Cuda is by NVIDIA, is really a dominating force in computer graphics card design. It's a very good company. You might want to look into them for employment or just what they're doing. They're always cutting edge. They have what I understand is a great corporate culture too. Would make a nice project, just somebody introductory course, just to research just NVIDIA, their culture, their products, their evolution, their market share. So Cuda is this C and C++ compiler libraries and runtime software to enable programs to readily access the new data parallel computation model and development applications. So you want to memorize that, what Cuda is, and look for that. Now, we'll come back to that in a second here. Scalable GPUs are scaling the higher transistor counts by increasing the number of constant performance cores on a die rather than increasing the performance of a single core. So in advanced courses with me, you'll learn about scalability in parallel processing and grain size and how different grain problems can be parsed into fine grain versus coarse grain, and different parallel processing hardware that's suitable for that.
You want to play some music, or are you working on stuff right now?
I have to finish a lecture. And then
I'll
here, for a comprehensive list and examples of current developments and applications that are accelerated by GPUs, visit Cuda Zone. So this is NVIDIA, and I'd like you to take some time here. This is the last slide other than the references. So after this slide, then please go and understand what Cuda is. And then finally here you see in 2020, GPUs have over 2,000 Cuda cores. So you can think of these cores as not want to say simple, but they're not full CPU kind of cores, but they are complex in what they do, and they're dedicated to certain functions. And you get in the order of almost 2,500 now, so over 2,000 CUDA cores. And so take a look at the link to CUDA in NVIDIA.